Okay, in this video we are using an ester to do a reaction similar to what we saw in the previous video in the malonic ester synthesis. The difference here is this is something called acetoacetic ester synthesis. What it really is this is called a beta keto ester. Alpha carbon, beta carbon, so the ketone is beta to the ester. The actual name I would not worry about. But I'm hoping you can see distinct similarities between this and what we had before. Before we started with a diester, now we're starting with a beta keto ester, so that should suggest the product, even if the mechanism is the same, should be different, because the starting material is different. We used our ethoxide to deprotonate at the highly acidic alpha carbon. So this alpha carbon is much more acidic than hydrogens on this carbon. And then once we have the enolate, we use the primary alkyl halide to halogenate there. And then we do our decarboxylation with H3O plus and heat. We get out carbon dioxide as we did before. Last time we got out 2 equivalents of alcohol. Now we get out 1 because we only have 1 ester group initially. So there's still a the reverse of a Fischer esterification involved, just on one side of the molecule. So overall, what this reaction is doing something rather similar to what the malonic ester synthesis did, except in this case, it's taking an alkyl halide, maybe the same one as we used before, and converting it this time into a ketone, but not just any ketone, a so-called a methyl ketone. Methyl ketone meaning one of the carbons coming off the carbonyl is a methyl group, so it's the end of the chain. Conversion of an alkyl halide into a methyl ketone, because these are particularly important functional groups, and in doing so, 3 carbons are added into the chain in the process. So if this carbon chain originally contains 3 carbons, the product will then contain 3, 4, 5, 6. All right. In terms of the mechanism, it's virtually identical to what we started with, or what we had in the malonic ester synthesis. So I'm not going to spend a huge amount of time on it, but let's draw out our acetoacetic acid. Oh, sorry, acetoacetic acid. That's this guy. And just as the malonic ester synthesis always started with that molecule called malonic ester, this acetoacetic ester synthesis always starts with this molecule. Got a nitrogen on here. Now bear in mind there are 2 hydrogens here. So you could actually get alkylation twice if you threw in enough base, right? You remember in the malonic ester synthesis the base we used was ethoxide. This is strong enough for a highly acidic hydrogen like this. It's not strong enough to deprotonate here. There's a stronger base we have to use for that, we'll see in another video. That's why we only get deprotonation here, we don't worry about deprotonation here, because this base isn't strong enough to do that. So here we go. Base grabs the hydrogen, forms the enolate, and in the last video I talked about you guys drawing out resonance structures for this enolate. So I'm going to go through it here, but I'm going to assume that you guys can do it. Here is one representation of our enolate. Okay. And then we have our alkyl halide. Let's say it's our 2 carbon alkyl halide again. Right? The electrons from the oxygen come back down. This bond breaks, and the electrons from this carbon attack the carbon from the alkyl halide. So far, this is literally exactly the same as what we did for the malonic ester synthesis. The only thing that's different is the ester that we started with. Otherwise, the arrows, the mechanism are both exactly the same. And it's still exactly the same here. Here we reform the carbonyl group. So we reform the ester, and in doing so, we have added those 2 carbons on. All right, that's our alkylated ester. So that is essentially step 1. All right. Step 1 was addition of this, then we add in the alkyl halide. In fact, I think this really doesn't need to have 2 steps. This really doesn't need 3 steps here. This has as the last step the addition of H3O plus and heat. It's really a second step, I should say, so I apologize for any confusion about that. Now, what happened to our ester last time we hydrolyzed it with acid? Well, it's exactly the reverse of the Fischer esterification like we saw before, and we get out our carboxylic acid. Right? I'm going to draw it out like this. And what we end up with is something that looks like this. We go from our carboxylic acid to, we go from our ester to our carboxylic acid. Alright? And then in the very last step, it's the decarboxylation again. The electrons on that oxygen grab that hydrogen, which breaks this bond here, forming CO2 at this carbon, which breaks this bond, puts those electrons on there, and then kicks those electrons back up onto the oxygen. And what we end up with here is, not only do we get CO2, but let's see what else we get. This carbon-oxygen bond is no longer a double bond, and that oxygen now has grabbed onto a hydrogen, so we know we have an OH here. So let's put that there. We have a methyl group coming off there, and notice that we have a double bond here. Double bond down to this. Now, what sort of functional group is this? Well, that's an enol. Right? And we've seen before that under normal conditions, the keto form is much more stable than the enol form. So what happens is this almost immediate tautomerization. We still have 1, 2, 3, 4, 5 carbons in our product. So let me just draw those out. I'm just going to draw it out kind of the way it is over here. Where the alcohol was originally, we have ketone, or we have the carbonyl, and that is our product. Methyl ketone, because there is a methyl group right on the end there. Because there was one there, and one there, and one there, and one there, and one there. Okay. Okay, I don't know if that little ping thing recorded there, but anyway, that's interaction for you. Okay, so that's the mechanism for a, not for a little blue dot, that's the mechanism for a acetoacetic ester synthesis. Alright? And if you can understand the malonic ester synthesis, then you are just fine. Notice that you add 3 carbons to the chain in the process. Let's just check. We had 1, 2 carbons in initially. Now we have 1, 2, 3, 4, 5. That is the malonic ester synthesis. Sorry, that's the acetoacetic ester synthesis. Notice that the two mechanisms are very similar. Alright, thank you.